Welcome to our analysis of UC Irvine's internal combustion Formula SAE Racecar. To begin, the brake calipers are safety-critical parts that are exposed to high load cycles and vibrations from the engine and road surface. To ensure that the calipers can withstand the high brake pressure load and translational loading from friction, static analyses were performed using the following various loads and boundary conditions. Looking at the worst-case scenario deceleration braking study, the original design was a simple brake caliper made of 6061 aluminum. This study showed the original part yielding due to thin cylinder walls and stress concentrations at the mounting holes. To resolve this, 7075 aluminum was chosen, the mounts were redesigned to alleviate the stress concentrations, material was removed in regions of low stress, and the cylinder walls were thickened. This resulted in a 17% weight reduction and a factor of safety of 3.3. An additional fatigue simulation was performed, showing no fatigue damage in the final iteration. All modal analyses will be reviewed at the end of the video.
For the brake rotors, it's important to consider the thermal effects in addition to the mechanical behavior when designing the part. A lower max temperature reduces the risk of deformation or the failure of other parts within the braking system due to overheating. The rotor was simulated under multiple conditions to help optimize the reduction in max temperature and reduce the maximum stress and deformation experienced by the part. The original design is already quite optimized, having many intricate cutouts within the geometry. In my first iteration, I increased the overall thickness of the part to be 0.25 inches from the original design of 0.1875 inches. This would affect the rate of heat transfer due to Fourier's law of conduction. In my second iteration, I reduced the cutouts and implemented vents within the rotor to assist in transferring heat through convection by increasing the surface area that could be affected by it. As you can see, the stress that the part experiences from thermal load is reduced with each iteration, and the maximum temperature is as well. Some drawbacks of the iterations are an increase in the weight, and with the second iteration, there is a significant increase in the complexity, which would affect manufacturing. Here's a summary of each of the simulations conducted for the part.
For the front wing of the vehicle, we need to make sure that the mounting is sufficient to withstand aerodynamic forces acting on it, as well as minor frontal impacts. The four cases of loads and boundary conditions are shown below. The boundary conditions differ between the upper mounting holes being fixed and the bottom spark connection points being fixed. Aerodynamic forces act on the plane were calculated using CFD, while side impacts act perpendicular to the surface. The original design is a simple rectangular end-plate made of a 5-ply composite material. The first iteration changes the geometry and the second iteration changes the hole locations. Both iterations optimize the hole locations, mitigating the buildup of strains. Max stresses and displacements were greatly reduced from the original. The additional simulation type performed in this part was a drop test simulating a crash. This is important since most crashes are frontal impacts directly affecting the front wing. The test was done at 20 miles per hour. The animation shows stress concentrations in slow motion. The max stress across all time intervals exceeds the yield stress at the point of impact in the upper corner.
The rear wing helped generate downforce to provide more tire grip, helping cornering stability. A static test will be run on the mounting system to ensure it can handle these downforces. The tube will then be isolated and put in a buckling test. The loading scenarios considered include a turning and straightaway simulation. These consider drag, downforce, and lateral loads calculated using CFD. The two different fixtures include configuration with fixed geometry, fixed hinges, and roller supports. The different iterations either thickened spar tubes or removed material from the skeleton. The first iteration did lead to better results. Removing the material in the second iteration weakened the structure and lowered the factor of safety by 0.6. For the buckling simulation, I either thickened the bar or made it shorter, both leading to an increase in the buckling factor of safety. And a closed-form solution was solved to see how accurate the simulation was, and the difference was basically negligible.
The solenoid mounting is the main component of our gear change system of our car. The bracket that holds the solenoid is connected directly to the engine. This part should be able to withstand the repetitive force required to change gear. For the static analysis, we fixed the part from the arm of the bracket and applied the load along the inner walls of the ring that holds the solenoid. We applied two sets of load representing the two options for solenoids that our team has. One solenoid only applies force along the inner walls of the ring, while the other one applies the force along the inner walls and at the bottom of the ring. After running the simulation on the original part, in our two iterations, we find out that our second iterations we has a thinner ring and a variable thickness along the arm, improved the factor of safety and decreased the weight as compared to our original part. In addition to the static analysis, we also perform a fatigue and modal analysis. The fatigue analysis also showed that the alternating stresses everywhere in the model are below the minimum SNN curve.
To summarize the modal analyses results, the engine rotational frequency at 250 Hz is of concern for the front and rear wing. The lower RPM ranges of the engine may excite the resonant frequencies for the rear wing mount, while the upper RPM ranges may excite those in the front wing mount. Ultimately, we use this design process in our iterations to improve our designs for the Formula SAE Racecar, which we will be using to compete this summer.